Haoyu Ren, I hope I said perfectly. Apologize if
it's
not.
Perfect.
Is a PhD. Apologize if not, but okay, fine. Is a PhD student at Technical University of Munich and Siemens AG in Germany since 2020. He has a BS in electrical engineering from Chongyang University and MS in electrical and computer engineering from the Technical University of Munich. His current research interests include industrial IoT, smart factory, tiny machine learning, and semantic techniques. Please, the floor is yours.
Okay, thank you, Danilo. Hello, everyone. I'm Haoyu, and as Danilo said, I'm a PhD student at Siemens and Technical University of Munich in Germany. And today, I'm going to talk about how to realize on-device learning on constrained devices in industrial IoT. So before I go into details how we exactly do that, I will first explain why we want to do this. And then I will talk about three major challenges that we faced in the past when we developing OD on-device learning, ODL solutions, and how did we tackle them. So the first challenge is IoT devices. They are really resources constrained. And the second challenge is how can we monitor the performance of the TinyML models in on-device learning? And the third is how can we scale up the solutions, because TinyML is not only about one device, it is about many, many devices. And finally, I will conclude the talk and with some future work. So machine learning has proved its value in many domains, and TinyML is a rising AI field that offers machine learning solutions at the edge on constrained devices. And because IoT devices, they are typically very cheap and applicable in different domains. So one of the advantages of TinyML is pervasive deployment. And there are also other key advantages, for example, privacy preserving, low latency, and high energy efficiency, because the sensor data can be directly digested at the edge, and we don't need to send all of them back to the cloud. But machine learning models are great when they work, but once deployed, their performance can often degrade over time due to model drift or concept drift or data drift. So when it comes to real industry environment, TinyML is really hard to do because a real environment is continuously changing. So the model you train this week might not work next week. And every machine is pretty unique. So even if they are of the same type and from the same manufacturer, so the model you trained using the data collected from one machine might not work for another machine. And we don't want to have angry customer. So the one way to tackle all these problems and helps the models to remain the high performance is on-device learning. So, but in the meantime, there are also additional challenges that comes with on-device learning. We should have something in mind that IoT devices that are designed to live long with limited resources, like 100 kilobyte memory, 64 megahertz CPU, and something like that. And there are not so many mature solutions in the market. Otherwise, we will not having this workshop today here. And finally, we have to agree that TinyML has a very fragmented ecosystem. So you can imagine that there are a lot of hardware or the boards with different sensors. And on the other side, we have different software, tool chains, and machine learning models. And we have to come up a way that can integrate all this together and scale up the solution. So for the challenge one, most TinyML approaches don't support on-device learning because IoT devices, they are normally very constrained. And so this normal methods like batch training will probably not work on the devices. So we propose the TinyOL, tiny machine learning with online learning to enable on-device training on microcontrollers. But first, what is online learning? So online learning means the data comes from a string and become available one by one. So the model there's one instance at a time. And this is somehow also aligned with running inference on microcontrollers, that the model will process the next input after finishing the last inference. So we propose a system that can be attached to an existing neural network model in microcontrollers. And it can act as a new layer or of the model, or it can replace the output layer in the model. So when the data stream comes, the TinyOL system, it will inference every arriving sample and then update the weights in the layer if a label is also available. And if the label is of a new class, so the TinyOL system can also modify the layer structure and then initialize neurons to accommodate the latest class. And as you can see here, the prediction and the training, they are somehow interleaved. So we don't need to save the data on the board. And once the layer, the inference and the training is finished, then we can discard the data once for all. And this makes this on-device learning very efficiency and doesn't require large memory. To assess this TinyOL system, we have designed several experiments. And the first experiment, we deploy an autoencoder with a TinyOL system on an Arduino board. And then we put a board on the USB fan to detect the anomaly vibration patterns from the USB fan. So here is some normal vibration patterns. It looks like that, 3 axes. And these are some abnormal vibration patterns. It looks like this. And the normal vibration data is used to train the autoencoder. And the abnormal data is used for evaluation. So what is autoencoder? So an autoencoder is an unsupervised neural network that trains to reconstruct the input data after compressing the data into an intermediate embedding. So by training only the normal data of the normal vibration data of the USB fan, the network should learn how to reconstruct the normal samples. And as you can see in the picture here, after the training, the normal sample can be very easily reconstructed, but not for the abnormal data, because autoencoder didn't see these anomaly samples during the training. So which means the reconstruction error on the anomaly data will be much higher. And these figures shows a collection of the reconstruction error of the normal data and abnormal data after the training. And we can separate the abnormal data from the normal data by simply setting some fixed threshold in between. But there is something very interesting. When we put the board with this trained model back to the USB fan, we find something here. And you can see in this middle histogram, the distribution of this reconstruction error between the normal data collected for training and the normal data collected after training, I mean in the field after the deployment, have a different distribution, although it's from the same USB fan. So why does this happen? Because when we put the board back to the USB fan, it is unavoidable. There are some deviations of the position exists. So it looks like the autoencoder is very sensitive to the position of the board. And so if we use some fixed threshold, like I mentioned here, for some anomaly detection, this algorithm might fail. And so in other words, we can say that we cannot guarantee that the training data and the inference data in the real environment have the same statistical distribution. So what can we do now? Then when we enable the TinyOL attached to this autoencoder, and then we fine-tune the layer in the TinyOL, and after some iterations, we then re-evaluate the reconstruction error. As you can see here, the reconstruction, after some fine-tuning, the distribution looks much better. And we also compared the time consumption of the TinyOL system. And we can see that the online learning just need about 10 more computation time compared to pure inference. So we also conducted some extended experiment under the supervised setting to show the effectiveness of the system, but I'm not going into the detail of this. So if you are interested, you can refer to our paper. And the takeaway for the challenge 1 is tiny online learning is one of the first solutions that makes undevice training on constrained devices possible. And for the challenge 2, as I mentioned in the beginning, that the model performance can degrade over the time due to the concept drift or the data drift. And so we can do the online on-device learning to tackle this problem. So the question remains here is, when should we trigger the on-device learning, and when should we trigger the retraining of the neural network? So to do this, normally we have to continuously monitor the model performance, and we can set some triggers to be some specific metrics that we want to monitor. And if the performance of the model drop below some predefined threshold, then we can trigger this retraining. Somebody might say that this is pretty simple because we just send it back to the cloud and there are many cloud solutions available for this. But in our case, IoT devices are constrained. So the communication is costly, is very expensive in terms of the energy consumption. So what we can do here is that we can also do continuous monitoring on device. And our solution is micro-CEP engine. So what is micro-CEP? CEP stands for complex event processing. And it is a well-funded technique that allows the user to use logical rules to detect spatial and temporal patterns in the heterogeneous streaming data. But currently, most CEP solutions are designed for powerful platform. So we have designed a tiny micro-CEP engine for IoT devices. As you can see here, different kinds of streaming data can be continuously pushed into the micro-CEP engine. And to be consumed by the micro-CEP engine, these data are first enriched into atomic events. And atomic events is the basic data unit in CEP. And on the other side, the user can define different CEP rules for desired patterns. And they can then upload these rules to the engine, and the engine will start to identify the desired patterns in this incoming streaming data against the rules that they uploaded. And upon the matching or upon the pattern matching, a complex event will be fired or triggered, or let's say some retraining trigger can be fired. And what's cool here is we also allow the user to update the CEP rules on the fly. That means the users have possibility to adapt the trigger criteria at any time. Next, I want to give you a taste of the CEP language and of our CEP engine. So as I said, atomic event is basic data unit in the CEP. And an atomic event normally has a name, some starting and ending time, and also a value. So these atomic events can be any sensor data and matrix and log data, but enriched with some name, time, and value. And what does a CEP rule looks like? For example, here are two CEP rules. And the first CEP rule is to calculate the average value of the last 10 machine alumni score events. And it will fire an event called smooth alumni score with the calculated value. And for the second rule means if an event smooth alumni score with a value higher than 1, then it will fire an event called warning. You don't need to know any grammar of the CEP now, because we also have the tools to help the user without any experience to construct this event and also the rules. Of course, there are also different kinds of rules are supported. For example, these rules, it is, oops, did somehow cover here. Okay, first rule is used to to describe a situation that within the 5 seconds, if an event called worker, if an event warning and the event worker occupancy state with a value 1 is presented, then an event called warning night will be fired. And so the message here that I want to say is that with the help of the CEP, we can combine different logical rules to formulate very complex trigger conditions for continuous for the continuous on-device monitoring. And we can even adapt these trigger conditions on the fly. And we have also shown the performance of the micro CEP on an Arduino board. So as the result shows here, its runtime is very small, and it can be easily fit into devices with limited resources. And we also evaluated the average throughput of several rules and operators, and also we evaluate the relation between the throughput and the number of the rules. So this test result shows that this engine can be easily used on constrained devices to handle very typical IoT scenarios, including the continuous monitoring. And the key takeaway for the challenge 2 is we lead some on-device continuous monitoring mechanisms here, and our micro CEP engine is implemented with a very user-friendly grammar, and it's very suitable for this use case. And the last challenge I want to talk about is that how can we scale up the TinyML solution, not only about on-device learning, but also the overall TinyML solutions, because we know that TinyML is targeting at many devices. So to deploy machine learning models on constrained devices, there is always a gap between the hardware and the software, especially the machine learning models. So on the one side, we have various IoT devices, and they are normally designed to for specific tasks with different configurations, like different sensors, memory, and platform. And on the another side, various machine learning models, they have been developed with different structures on different tool chains. So and all this and these machine learning models, they are normally distributed as some binary files you can see here, without any standardized or cleared description of their working principles. And so all this leads to a very fragmented ecosystem. And there are some questions we might be interested in and we want to address here. For example, if you give me a neural network, I want to find out which IoT devices can support it. And if you give me a device, I want to discover which neural network or the trend available neural network is, or even on-device learning algorithm is compatible with this device. And how can we manage all these elements and reuse these components at scale? So to do that, we proposed the semantic-based management of tiny machine learning. So first, we introduced an ontology for describing neural network models in the context of TinyML. You can think this as information models for presenting neural network. And for instance, we can use this information model to describe the metadata, structure, and hardware requirements for neural network model. And this information model is also designed to be aligned with W3C scene description. Scene description is a standardized information model to semantically describe IoT devices, for example, their hardware specifications. So with these two information models, then we can describe TinyML components in a unified language. So this is our proposed framework, and it starts with describing the TinyML models and also embedded system against the information models that I described previously. And next, we can store this knowledge, the knowledge about the models and devices in a knowledge graph or graph database. So with this, we make all these knowledges about this ecosystem of the models and devices manageable and also searchable, just like the web resources. And the developers can use various query to discover and reuse TinyML components. And even to matchmaking, for example, matchmaking devices with ML models. And eventually, they can also deploy the models to the devices upon the matching. So as an example here, this is a very simplified small knowledge graph with only 23 publicly available TinyML models and also 6 IoT devices. So the ML models are shown on the left side. And in the middle, there is a model called Move is expanded. And there are 6 embedded devices shown on the right side. And we can see that the graph database offers the advantages in presenting the relationships within this within the complex TinyML system. And with this knowledge graph, we can already realize a lot of interesting things here. Using we can use Sparkle queries to realize these interesting functionalities. The Sparkle query looks very similar to SQL query. And for example, the first query means I want to find all the compatible devices, giving a model. And query 2 is giving a model. I want to find all the compatible models. And query 3 means we want to benchmark the machine learning models for a specific task. Of course, I believe most of you have no ideas of Sparkle queries. So we integrated this system as a service into a no-code platform. And we have created also a tool to help the users to search these components, and just like some Google search or Microsoft search. And also they can do different matchmaking. And you can see here some filters can be applied to further refine the searching results. And we welcome any contributions if you are interested. So for the conclusion and future work, Tiny on-device learning we believe it's still in its early stage. So we have to develop different novel techniques to tackle all these issues that I mentioned before. And we have proposed or implemented TinyOL, MicroCP engine, and semantic management system to try to push the community, to try to push this research area a little bit forward. And for the future work, we believe tiny federated learning is very important, because as we discussed that, as we said that TinyML is about many devices. And we also need to be very careful when developing on-device learning, because the microcontrollers, they have very reduced numerical precisions. For example, we can do 32 bytes floating computation on the laptop, but on the microcontroller, it's only 16 bytes. And the next future work might be some benchmark, because some of you might know there is a benchmark called MLPerf inference benchmark that is designed for benchmarking the TinyML devices for inferencing. But to scale up all the solutions, we need some benchmarks that can also test the on-device learning. And I hope this will happen in the near future. And the last but not least, the collaboration, as I believe, is a key for the future advancement. And that's all for my talk. Thank you for your attention. I look forward to your questions.
Thank you so much for your great talk. I think you shared through the 3 challenges a broader view on the on-device learning. And thanks also to mention the need for benchmarking. I think this is a quite important point. Thanks for that. There are several questions in the Q&A chat. So let me start with the first one. We will try to address all of them. If not, if time permit, if not, please go through the others remaining, typing your answer. First, I am a bit confused. Why don't we need to save data on board in TinyOS model? Can you tell on revised learning again?
Yeah, so we know that this TinyML devices or IoT devices that are normally pretty constrained. And you can imagine that if you want to do some image classification, each image might be 28 times 28 pixels. And so with 100 kilobytes memory, it's not possible to store. I mean, maybe we can store like up to 10 pictures on the board, and that's all of it. So it's not possible for us to do some batch training to save a lot of data on the board to do this normal approaches. Yeah.
Thank you. Second question. In a previous paper with Siemens 2021, maybe you mentioned that for INNs, it's not easy to use them to infer the spatial and temporal context, so manually coded micro CEP is needed. Is this not becoming possible with models like transformers? For example, to create an auto CEP on a server in the monitoring room?
Yeah, that's a great question. So yeah, that is possible with transformers. First is that transformer is pretty huge models that is very hard to be fed onto the IoT devices. And second here, what we want to address with micro CP engine for the on-device learning for this topic is that we want to trigger, want to have some retrigger, we want to have retraining triggers for this. And we believe that micro CP is one of the candidates for this problem.
Thank you. Next one, quite practical. Is there code available for the TinyOL implementation on the used Arduino boards?
Yeah. It's very difficult to share the code externally with some third party, but we are glad to help you if you have any problems when you implementing the code. Yeah.
Thank you. In macro CP, it looks like the neural network and symbolic logic are not jointly trained or optimized. How does your framework fare with those CP frameworks where the network and logic are optimized jointly? For example, the logic is differentiables, like deep prob log, near deep CP, etc.
Yeah, that's a good question. So in this on-device learning area, we basically treat this system, the neural network and also the CEP, as two independent systems. And what the CEP do is that it can use some user can use some rules to define some trigger conditions. And once something happens and once some matching upon the matching, so it can trigger the retraining. So basically for this area, we are not thinking about how can we combine them together, but you are right. So there are also this is a very active area that people try to have some neural network method to develop some CEP rules. Yeah.
Have you considered the paradigm of continual learning as a candidate for on-device learning?
Yeah, of course. because from the challenge one, we have the key takeaway that on-device learning, we believe, is one of the solutions that for the future. I mean, our TinyOL, Tiny Online Learning, is one of the candidates for the on-device learning, and we believe it will be a candidate also in the future, and it has a very good potential, and we are still working on it. So stay tuned.
Thanks a lot, Haoyu, for your time. Great talk, for the availability to stay with us. That forum was possible thanks to the TinyML Foundation support and all the support from the strategic customer, which are helping a lot in providing resources to make sure that this forum and other events and other interesting events will happen in the future. So just to thanks also and list the executive strategic partners, ARM, Edge Impulse, Qualcomm Research, Sentient, and the Platinum Strategic Partners, DeepLight, Click-Attack, Reality AI, Renesas, Sony Semiconductor, the Gold Strategic Partners, Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, Sensimil, ST Microelectronics, Synaptics, ScienceSense, and all the silver strategic partners. Thanks again to stay with us yesterday and today, and I hope it was a valuable experience. Thanks and see you soon. Bye.